Now we are going to look at the mean square error and the bias variance trade-off. Remember, we had the risk function given as this expression. The integral expression here denotes the expectation value of the loss function. Now, let's define y as the true value and f hat of x naught as the estimated value evaluated at x naught for this value of y, which is the true value. We can now calculate the expectation value of the square error loss. The expectation value of the square error loss is given as the expectation value of this expression in here, which is the true value minus the estimated value at x naught squared evaluated at x naught. We can now work out this expression and you will get the following expression. This term here is the irreducible error. This term here is the square of the bias, and this term here is the variance. Now let us inspect each of these terms separately. Remember, the irreducible error is this first term. It comes from the variance around the true mean inherent in the data. It is very difficult to get rid of the irreducible error, hence the name, through the modeling process. We have also seen how bias and variance plays into how one can select a model. For non-parametric models like histograms and kernel density estimators, in lesson 3, we discussed the role the bin size or bandwidth plays in determining the variance and bias of the model. Our goal is to minimize the square error loss. This in turn means that we are minimizing the bias term or the variance term. The problem is minimizing both is not always possible due to the complexity of the model. We will look at this problem. Thus, we have a situation where we have to have a trade-off between minimizing the bias square or the variance term. This is what is referred to as the bias variance trade-off. The goal in statistical and machine learning models is to minimize the loss function and in turn the risk. You may recall from an introduction to machine learning class how the cost function was defined and minimized to converge to a model. Notice it is simply the use of the least square loss function. Although we often choose the square loss in statistical learning, you must understand that you are in complete control of the way you choose your model through the choice of the loss function. Our decision is also based on how well we want the model to fit the data measured by the variance versus how well we want the model to generalize to new data, which is measured by the bias. Remember, there's always the bias variance trade-off. The cost function can be calculated on the training dataset, the validation dataset, or the test dataset. Minimizing each of these cost functions serve to optimize the model for different purposes. Let's take a look at the cost function calculated on the training set versus this test set. The following example is taken from a book named The Elements of Statistical Learning. Please see the instructor's notes for more details on the book. Let's take a look at the following diagram. What we have on the x-axis here is model complexity. Think of it as the number of variables in your model. On the y-axis, we have the prediction error. The red lines here represent the error calculated on the test dataset. The blue lines here represent the prediction errors calculated on the training dataset. Notice how the error on the training dataset reduces as the complexity of the model goes up. However, this is not the case for the prediction error calculated on the test dataset. The solid curves here represent the expected values of all the prediction error curves. The model complexity can be thought of as the number of features in the model being used. Intuitively, you may already have an idea of how the number of features can affect the way your generalization or prediction error can be affected. A less complex model with a low number of features will have low variance and high bias, and we might end up underfitting the model. In contrast, a more complex model will have high number of features, resulting in high variance, a low bias, and thus will be overfit. Remember always the trade-off between the bias and the variance. In the next video, we will try to quantify the complexity of a model and look at bounds on the training and test errors that we can calculate on the samples.